Thank you, Stefan, and thank you, the organizers, for this beautiful workshop, for wonderful talks, for wonderful weather. Next time, please make sure that the weather in Toronto also stays nice so I can get here. So what is the reason for my topic and for these dates? I carefully read the description of the workshop, and I noticed that it's a continuation of the program, long program at IPAM in 2007. And that was the title of my talk there. Well, I gave a few talks there, but that was the title of the talk, the main talk that I gave. So I decided that, well, okay, let's talk about what happened between 2007 and 2026. And this is based on joint work with, well, these people. Mark Braverman is now in Princeton, Adi Glucksam, she's in Hebrew University, Cristobal is in Chile, in Pacific something, and Michael is my colleague in Toronto. So unfortunately, I will have to start with a crash course for this audience. Some of you have seen versions of this before, so this would be a good time to doze off. Then I will quickly discuss what we knew in 2007, and well, I was trying to remember what I was talking about in 2007, and I will describe what we know now, and what is left. Well, this is way too ambitious, of course. Nothing is really known, as you will see, but there are lots of interesting immediate questions. Okay, so that's the plan. And again, let me start with a crash course. So what do I mean by computability and complexity? So let me start with computability. And well, this is not a very rigorous definition, so I hope there are no logicians here, because, well, the department there has some logicians, so I hope that they didn't come here, because the definitions I would give are really not that rigorous. So a function for me is computable if you can describe it by a program. So if you can write a program, well, formally speaking, a Turing machine, which you input n, it outputs exactly the value f of n. And the set is called computable if you can compute its characteristic function. Now let me give you an explicit example of non-computable set. Well, this is from Wikipedia even now. It's what is called halting set. So you enumerate all the Turing machines, all the programs, and you put your number in the halting set if the ith Turing machine halts. And then it's a very easy thing to see that you cannot compute this set, because the program, algorithm which would compute the set is should halt or not halt. But the set is called low computable if you can find the algorithm which enumerates it. So if you input n from the set, it halts, and if you input n not from there, it never stops. So this is called low computable. And yeah, it can verify inclusion, but not exclusion. And this is an explicit example of low computable set. It's actually very easy to check. Complement of low computable set is upper computable, and set is obviously computable if it's upper and low computable. And of course, you can replace natural number by every explicitly enumerable countable set. Not only you want it to be countable, but you want to have a function which enumerates all the elements of it, like q to the d. Okay, now, of course, we don't want to just deal with countable sets. So what is a computable real number? Well, that's a number for which you can find a function, a computable function, a program, which would on input n, output a 2 to the minus n approximation to it. And now number, real number, so now d is equal to 1, is low computable if you can output a sequence which converges to x from below, upper computable from above. Why this is not the same as this? Of course, because you might not know the rate of the convergence, and that actually happens. One remark here is that there are only countably many computable points, which makes my next definition very difficult, because I want to now define computable functions. don't want to define computable functions just in computable points. I want to define computable functions as functions. So what are they? For this, I need Oracle. So again, this definition is very similar to this, but the main difference is that here, there is an algorithm which does it. Oracle is just a function, just some God-given function, Oracle, which on input n would output 2 to the minus n approximation to x. And of course, 2 to the minus n, this is all notation-based. So you can pick any sequence here which tends to 0. And now, what is a computable function? So suppose that you have a set, and function is called computable. If there exists an algorithm which, given an oracle for a point in S, and input n, would output 2 to the minus n approximation to f of x. So what this algorithm can do, it may query an oracle as many times as it wants, but finitely many times. This is very important. So at some moment, it has to decide, OK, I know this point well enough. I can stop, and I can just output the value. So because of this, all computable functions are continuous on the domain definition.
Ilia.
Yes?
So S is a subset of RD, but it's valued in RK?
It's valued in RK, yes.
Okay.
So yeah, and again, this all can be generalized, of course. So you don't really, you can talk about computable compact sets and all this stuff. Let me not dwell there. For me, K would mostly be 2, and D will mostly be 2. Any questions about this stuff? OK, now, very quick excourse in dyadic cubes. So dyadic cubes, yeah, you partition RD in the cubes. And then connected interior finite union of dyadic cubes is called dyadic polygon of rank M, if the size of the cubes are same size. And of course, if you have dyadic polygon of some rank, it's also dyadic polygon of bigger rank. And we do not assume that they are convex, simply connected. Holes are allowed. And why I would want it? I would want union of 2 dyadic polygons, which have intersecting interiors, to be again a dyadic polygon. And now our first excursus in uniform something. A sequence of dyadic polygons is called uniformly computable if there exists an algorithm which input n, and the size 2 to the minus n would output the description of this polygon Pn. OK, so now I can talk about computability of subset of RD. So an open set is called low computable if you can find an increasing sequence of dyadic polygons whose union is Pn. So find meaning there is an algorithm which on input n would just give you this polygon. And set is upper computable, of course. Compact set is upper computable if its complement is lower computable open set. Now, compact is called lower computable if you can enumerate all the polygons which intersect this set. So this is, again, a somewhat fine point, because this is uniformly computable sequence. But why is it low computable? Because it only enumerates them. So if I give you a polygon which is not there, you would never know it. It would just never appear in this sequence. But it will eventually, if the polygon is there, if the polygon intersects your set, eventually it will appear in this sequence. And compact is called computable if it's simultaneously lower and upper computable, and this is a horrible definition. So this is a much better definition. It's when you can output a sequence of dyadic polygons that converge to E in terms of Hausdorff distance. I don't think I have to define Hausdorff distance here. So basically, when I talk about this in computer science audience, I just tell them, okay, so you can draw set E on computer screen with arbitrary precision. That's what computable compact set is. And another equivalent definition is that distance function to E is a computable function. That's equivalent to the set being computable. Okay, so of course I will talk about measures too. And so what is a computable measure? It's basically when you can compute every integral over every dyadic cube. So given a dyadic cube and sequence of uniformly computable functions, you should be able to output a rational number which approximates this integral. So they can be algorithmically approximated by sequences of delta of linear combinations of delta measures on rational points with in the weak sense, and this is the same. And functions f, you can just take them to be computable one Lipschitz functions, or even smooth functions, or even smooth subharmonic functions. So you don't really need this for arbitrary sequences of uniformly computable functions. So it's enough to consider smooth subharmonic functions. And now, what is a uniformly computable family of measures? Well, again, this is, you give me value of x by an oracle, I compute you mu of x. So there should be one algorithm which does all of this for all x. So oracle for, I can query oracle for x and give you the measure. Okay. Now, okay, before I go next, any questions here? Yes?
So why is this 2 to the negative n that you see in all of these definitions? Is this really important? Like
no, not at all.
By 1 over n.
I like 2 and I like exponents.
So just like
any explicit sequence which goes to 0, or strictly speaking, every computable sequence converging to 0 would work here. It gives exactly equivalent definition. In 2007, all the talks included 10, but then I realized that it's much easier to write 2. Now, this is, again, here I really hope that no logician is in the audience, because this is really just a description of what it really is. So, complexity. Well, these two classes are probably known for everybody here. So, P is the class of problems which are computable in polynomial time in the length of input. So you give it n bits, it computes the solution in polynomial time. NP is whether you can check the solution in polynomial time. Now, next classes are much more esoteric. So let me start actually from here. This is exp is easy. So this is solvable in exponential time, and it's really not just 2 to the n. It's 2 to the n to the some power. So it's really like huge time. It's a huge class. And let me restrict now here. So these are guys from exponential class, problems from exponential class, which can be solvable, but you use only polynomial space. So you use polynomial amount of memory. And finally, sharp P is even more exotic. So what is NP? So there is famous theorem of my colleague Steve Cook, which started all this business, that every NP problem can be reduced to the following problem. I give you a proposition formula with n Boolean variables. Tell me whether this proposition formula has a true assignment. So is the assignment of these Boolean variables such that the formula gives you the truth? So that's what is called an P-complete problem. And sharp P is exactly the same problem, but now you give me a proposition problem, a proposition formula rather, and I ask you how many times it is true. So it has 2 to the n possible assignments of true falses. So how many of them gives you truth? So sharp P is this class. And the only thing known here is that P is not equal to EXP. And that's not an easy theorem. That's, I don't be, well, again, in 19 years I should have learned who this theorem is and who is this guy who, in these 19 years, received Turing Award for this, but I don't remember. And this is recorded on YouTube, oh my God. Okay, anyway, so what is conjectured is that all these classes are different. Again, P is not equal to NP, this is $1 million problem, but all of this are also interesting. Okay, so I hope nobody asks me for clarification for this, because again, this was just, if I start to do it rigorously, it will take me another few hours, so let me skip this. And now let me try to explain what we knew back in 2007. So, first question is, suppose that I have a domain, simply connected, of course, on the point inside, and what do I need to know to compute the conformal map from the unit disk with positive derivative at a given point inside the domain. So I need an algorithm that, given a point in the disk, would compute f of z with arbitrary precision. What should I know about omega? And actually, the answer to this is very satisfactory. This is what is called constructive Riemann mapping theorem. In this form, it belongs to Hertling, and it's from '97. That basically, f is computable, and f inverse is computable, if and only if both omega and d omega are both lower computable. I don't know why I have a bracket here. So let me just quickly tell you the idea. So suppose that it is low computable. So you find the sequence of dyadic polygons, you compute maps to these polygons. Of course, these maps converge to f, because these polygons, of course, Carathéodory converge to omega. But how do you know that they converged closely enough so that you can say, okay, this gives me value f of z with given precision? Very easy. You just approximate the boundary, and it gives you a rate of convergence. And other direction, it just follows from the distortion theorems. So if you can compute this map, you can, just by using distortion theorems, you can easily compute this sequence of polygons, and then you can easily compute, well, the boundary from below. Okay, so again, that was the topic of my talk, again, 2007. And this is about how difficult it is now to compute this. And suppose that you have an algorithm that, given a simply connected domain with nice boundary, so not just low computable, linear time computable boundary, point inside, and the number n, suppose that it computes 20 n digits of conformal radius. As we know by, again, distortion theorems, computing conformal radius is the same as computing just f of z at every point. Then, the theorem says, we can use this algorithm to solve this SAT-n problem, which I mentioned, in linear time. So, in other words, this problem is sharp P complete. Okay, so let me just very briefly say, because now it sounds extremely esoteric, let me explain what it is really all about. So suppose that I give you a propositional formula. And this L would be, corresponding set of numbers. You just think about them as n-digit binary sequences. And let's just look at this exciting set. So you take unit disk, and you remove very small little disks at the points corresponding to the points where this formula is satisfied, where it gives true value. And the key estimate here is that the derivative of the conformal map from the disk to this domain, of course, doesn't care where these points are, where these little disks are located. It just cares about their number. And so that's the estimate. That you can, knowing conformal radius with the 20n binary digits, you can actually compute the number of Ks. That's it. And of course, you can compute this boundary using this propositional formula. That's trivial. And so you can just evaluate size of K and solve this problem. That's all. Now, other direction, unfortunately, was slightly more difficult. So what happened there? I said that the problem is sharp P complete, meaning that every problem from sharp P can be reduced to the problem of computing conformal radius of this map. But can you actually compute the conformal radius in sharp P time? So unfortunately, we only knew in 2005 of an algorithm which would compute this value with precision, with this complexity, with precision n, with complexity P space of n. And the algorithm was extremely stupid. So, well, we all know that conformal maps can be reduced, computing conformal maps can be reduced to solving the Dirichlet problem. And how do you solve the Dirichlet problem? Well, you just do random walk. And then there is magic in computer science that tells you, oh, if you have a random algorithm, an algorithm which uses random bits, which would compute your value in expectation, then you can de-randomize it. There is an algorithm with relatively small overhead, which would compute it in essentially the same space. And of course, for random walk, if you think about it, you don't need too much memory, right? You just need to know where you are now, where you are at this moment. You don't need to remember the past. So random walk is exactly small space, big running time. So that's exactly what we want. So it's de-randomization, but the randomization just gave us P space. And the reason for this was that if you think about it, well, how would you compute? How would you solve the Dirichlet problem? You would run your random walk till it hits epsilon neighborhood of the boundary. And then you would say, oh, OK, you hit epsilon neighborhood of the boundary. By Berling's theorem, you almost solve the Dirichlet problem, so you are done. But of course, how long would it wait? Epsilon to the -2 on average, right? Because to reach this level, if you have a domain, each step is epsilon. So yeah, epsilon to the -2, it's a huge number of steps. So for precision 2 to the -n, you need 2 to the -2n. That's horrible. So, well, how to deal with it? Of course, you want to solve the Dirichlet problem faster. And that's where we are moving to what we know now. So this happened after 2007. And this is walk-on-spheres algorithm. I don't pretend that this algorithm happened after 2007. That was, that was known to Kakutani. There is a first computational paper about this is by Miller in 1950-something. And the idea is the following. Instead of just running random walk, you know that you are solving the Dirichlet problem. So you are trying to approximate Brownian motion. So why not just run Brownian motion? You know what you can do. You can just take a point, take half the distance to the boundary, and uniformly pick a point on this disk, and then continue doing this. This way, of course, you hit the boundary much faster. If you think about it for a second, you think, oh, of course, it's probably logarithmic time. It's not. And so, when this amazing idea hit Mark Braverman. I first said, okay, what do we do with discretization? Well, we managed to do something with discretization. So at this moment I said, oh, sure. Of course, people thought about it. So they know how fast it converges for simply connected domains on the plane. Well, what can be easier, right? Well, so when does it reach epsilon neighborhood? And so the problem was that we couldn't find the reference. More than that. So the reference was known for convex domains. There were some obscure papers in Russian where it was known for some domains with some strange conditions, but not for general simply connected domains. Well, not to worry. That's what defines rate of convergence. So we call domain alpha sig. So now we are in RD. If for any point on the boundary and for any small enough r, Hausdorff content, so not measure, but alpha, d minus alpha dimensional Hausdorff content is controlled. So there is some uniformity there. And then the theorem, which is not surprising at all, tells that, yeah, when alpha is less than 2, the rate of convergence is what we want. It's logarithmic. When alpha is equal to 2, it's square logarithmic. And when alpha is bigger than 2, then it's this. Now, again, if you think about this for the moment, why I'm saying that it's not surprising, because this is exactly where it stops being regular. So when alpha is bigger than 2, you cannot guarantee any longer that your domain is regular. Even when alpha is equal to 2, some regular domains are exactly 2 sig, but others are not. But when alpha is less than 2, all domains are regular for Dirichlet problem. Great. Including, of course, all simply connected domains. All simply connected domains are 1 sig because complement is connected. So this is great. And this is precise description of everything. And so, yes, so 1 sig, so we need only this number of random bits. Okay, now I don't know how do I say it on YouTube, because this is a sticky point now. We got so excited about this. We liked the technique that we use there, that we completely forgot about the original problem, that we really just didn't state it. So now it's a theorem of Rattinger, who luckily noticed it and wrote down all the details. It's not a trivial work at all, but again, we should have done it. We just forgot about it. That now we know that actually sharp P is precise. That computational complexity of computing conformal map at an interior point is exactly sharp P. So this is a sharp P complete problem. And if anybody here wants to get, well, not $1 million, but something to prove that sharp P is not the same as P, you just need to show that you cannot compute this in polynomial time. That you can compute conformal map in polynomial time, and then you are done. Because this is now, again, sharp P complete problem. Okay, questions here? Okay, now, what else do we know? The next thing is, well, revisiting classics. It's, well, very classical Carathéodory theorem, which says that if you have a simply connected domain, then this map extends to a continuous map up to the boundary if, and only if, the omega is locally connected. And here's the definition. A set is called locally connected if it has a modulus of local connectivity. So this is non-decreasing function, such that if 2 points are close enough, then you can join them by a connected subset of K with some diameter which is less than m of delta. So this is definition of modulus of local connectivity and local connectivity. Now just a reminder that it extends to homeomorphism if and only if domain is Jordan. Okay, so what was the motivation for this paper with Mark Braverman and Michael Yampolsky? I actually received the paper to referee. And the question was, which was asked there, what information about omega does one need to compute f up to the boundary? And the paper proved that this is true if and only if modulus of local connectivity is computable. How do I say it? Again, I'm saying it on YouTube, horrible. The paper wasn't even wrong. So I became interested in this question, asked my colleagues, and that's actually what happened there. Yeah, this is definitely wrong. But what we need is an object which is familiar to, well, complex analysts here. This is what is called Carathéodory modulus. So instead of just looking at 2 points which are close to each other, you look at points which can be connected by a crosscut. So which are 2 points on the boundary which are close inside the domain. So if you can connect them by a crosscut of diameter less than delta, then you look at the connected component of omega minus gamma not containing W0, and the diameter should be bounded by this eta of delta. Of course, eta of delta is less or equal than m of delta, but when delta tends to 0, this is equivalent. Eta of delta exists if and only if m of delta exists. That's really easy to check. And actually, if you look at modulus of local connectivity of the complement of omega, then they are related. So eta of delta and m of delta, again, there is only inequality here. With modulus of local connectivity of complement, there is this inequality, which is really easy to check. And the real theorem there is that, oops, I even misquoted my co-authors here. So this is a paper with Cristobal Rojas and Michael Yampolsky. So Carathéodory extension of a function is computable if and only if the function itself is computable, and we know what it means for omega. So by constructive Riemann mapping theorem, it means that omega is low computable and the boundary is low computable, and there exists computable Carathéodory modulus. And this is precise. There exists a domain with computable Carathéodory modulus, so this is computable, but no computable modulus of local connectivity. Okay, so we can actually say a bit more there. So this is Carathéodory metric. So distance between 2 points now is infimum of the diameter of anything which separates these 2 points from W0, and it can be cross-cut or a closed curve. And then you can extend it to W0 just by continuity. And closure in Carathéodory metric is called Carathéodory compactification. So this is the one obtained from omega by adding prime ends. And so this is not our theorem, this is an theorem. Oops. This is Carathéodory theorem. This is, yeah, I like that. Okay. Can I remove my consent from YouTube? So this is Carathéodory, of course. So the year is not 2014, more like 1914. But in 2014, we proved that actually if you have oracles for W0 and for the boundary, and for oracle for boundary, I mean that you can produce an approximation of the boundary, but not necessarily by something computable, by just something. So you have this sequence and you can query it. Then you actually can compute both this homeomorphism and its inverse. And what I like about all this abstract stuff, that actually you only need to compute this, because computability of the inverse is free. If you have a computable compact, you have a computable map between computable maps between two computable compacts, then inverse is automatically computable. So you don't have to prove anything. Okay, so now let me very quickly talk about the proof of it, so that you see that it's not that complicated. So, well, we can look at oscillation of f near the boundary, and then there is this great theorem of Warshawski, which relates Carathéodory modulus and oscillation. So if you have a domain of area A, and you know its Carathéodory model, you can compute the oscillation by this formula, and this is just very easy consequence of false lemma. And then, of course, if you know this oscillation, you can first compute the value here, and then use it to compute the value here. So in the other direction, we needed a refinement of classical Lavrentiev estimate. Well, again, most analysts in this audience probably know this as a Berling estimate, but actually it's due to Lavrentiev. He proved it first in 1936. But then again, many people reproved it. We needed a refinement of this. So basically, it says that in this Carathéodory metric that I defined, inverse of Riemann map, so the map from domain to the disk, is 1/2 Hölder, but we needed it with constants. So if you have if your point is far away from the boundary, then diameter of the pre-image of what is mapped there is bounded by essentially square root of diameter of the crosscut. Well, again, with constants here. And of course, after this, you can easily, so if you have computable F, you can easily compute the Carathéodory modulus. Okay, so now, okay, look at the time. Let me quickly tell you an example of set where you can compute Carathéodory extension, but cannot compute local connectivity. So what you do, you take any low computable, non-computable set, say halting set, and look at these points, and basically do the following. If you have point not in B, then you add a straight line from xi1 to xi. And if I is in B and it has number S, so then what you do, so this is, well, you remove this little fiord of this size. And so this is your domain. And then I can tell you, well, why it is computable. It's very easy. You run an algorithm enumerating B for S plus 1 steps. For all those i's that have been enumerated so far, you draw corresponding fiords. For all others, you draw I line. And that's, yeah, you know everything up to the 2 to the minus S. So this is very much computable. Carathéodory modulus is very easy to see. It's 2 square root of R. Because if you have point here and point here, that's the worst that can happen. So these points are at distance R, so this is about 2 square root of R. But what about this modulus? You see, the problem is that if you can compute connectivity modulus, you would be able to say whether these 2 points were on the other side, either on 2 different sides of this field, or whether this was actually 1 point. So basically, this is the precise way you do it. So you compute Ri such that this holds, that it's less than xi over 2. And so if I is in B, then I is enumerated in fewer than Ri steps. So I just propose you an algorithm to compute B. So you just run this for Ri steps, and you know whether your I is in B or not. That's it. Okay, does it make sense? Questions? Okay, now, in the remaining few minutes, I still have 5 minutes, right? Perfect. So now harmonic measure, my favorite object. So if you have a planar simply connected domain, then actually computing harmonic measure is the same as computing conformal map. So, and there is a precise connection there. So all these four conditions are equivalent. Omega and d omega low computable. For any computable W naught, the conformal map and its inverse computable conformal bijections. This equivalence is, of course, we saw it. Then this omega has computable harmonic measure at some point inside, and omega has uniformly computable harmonic measure. All four are actually equivalent. And the moment you leave realm of simply connected domains, things are much more complicated. So there exists a bounded regular domain, not just with low computable boundary, with computable boundary, for which the harmonic measure is not computable at any point inside. So of course now the quest is, well, how do you characterize the domains where you have computable harmonic measure? And that happened a bit later. So now notion of computable regularity. So, well, of course, everybody knows this point is regular if for continuous function on the boundary at this point, Dirichlet solution is also continuous. Another way to describe it is the following, that for every n there exists epsilon, such that if you are epsilon close to this point, then harmonic measure from this point of this ball of radius 2 to the minus n is at least 1 minus 2 to the minus n. So that's yet another definition of regular point, and the definition of computably regular point. So omega is called computably regular if you can find this function epsilon of n. More than that, it's explicitly computable positive function epsilon of n, such that if distance from x to the boundary is less than epsilon of n, then harmonic measure of this ball is at least 1 minus 2 to the minus n. So any computably regular domain, of course, is regular, and any simply connected domain by Berlik projection theorem is computably regular. And this is yet another class, so let me just say that, well, okay, uniformly perfect domains by theorem of Pomerenki, they're also computably regular. And now for computably regular domains, actually exactly the same is true as for simply connected domains in the plane, and here we don't need to be in the plane any longer. So here omega and d omega are both lower computable. Omega has a computable harmonic measure for some computable point, and omega has uniformly computable harmonic measure. This is all equivalent. So if you have computably regular domain, the moment you are able to compute the domain and boundary, you can compute harmonic measure and you can compute it uniformly. More than that, if boundary is computable, then computable regularity is actually necessary. So if boundary is computable, then domain is computably regular, is the same as it has computable harmonic measure at one point, and the same as has uniformly computable harmonic measure. And of course, regularity is important here. You know, you remove 0. Yeah, it's domain with computable boundary, but definitely not computably regular because it's not regular. But unfortunately, there exists a low computable domain with low computable boundary, uniformly computable harmonic measure, which is not computably regular. So this is not exactly if and only if that we were looking for. Okay, we looked further. Now, this was really surprising thing for us. If you have any domain, and you have point inside, and you manage to compute harmonic measure at one point, then you're able to compute harmonic measure at every point. And it's not that difficult, as it turns out. But on the other hand, there exists a regular domain such that, well, it has computable harmonic measure at every point. So you give me x. There is an algorithm which would compute harmonic measure at x, but you cannot do it with one algorithm. So if you restate it in terms of solving the Dirichlet problem, there is a computable simple function, meaning that it takes only values 0 and 1, such that the solution to the Dirichlet problem with boundary data satisfies the following. For each x, the value of x, of u of x, is computable at this point x. So there is an algorithm which computes this value, but u is not a computable function. So I spoke to real logicians, and they say that this is probably one of the first examples of wild appearing of such functions. So a function which is not a computable function, such that, again, it's computable relative to x for all x. It's very easy to just construct it, just from combinatorially, but this is the first time they saw it appearing in real life. Okay, so, but now, uniform computability. So suppose that you have a domain which has a computable harmonic measure at x0 for some computable x0. Then omega has uniformly computable harmonic measure if and only if omega is low computable. So you can go, oh, and I ran out of time. Sorry about that. Okay, so this is what left to be done. Homework for the auditorium, you'll be tested at the end of the workshop. So it needs all needs to be solved. Alec, where are you? Yeah,
I'm here.
Yeah, we need to finish writing this. Okay, thank you.